No, we are ready.
It's me. It's me.
Whoever me is, you are disturbing the class. Shoyinka.
Rather those.
Okay. Are we going to do this again today? Please mute yourselves, all of you. Where's my recording? Okay, good morning. Share screen.
Good morning, ma.
Good morning, ma.
Good
morning.
I can't see share screen. Oh,
Good morning, ma.
okay, so we started talking about enthalpy change, and then we said that enthalpy, the absolute value, cannot be measured, or it's not that it cannot be measured, sorry, it is difficult to measure. One of the ways to measure it is calorimetry and to use Hess's law. So let's dive into calorimetry. So this is generally defined as a science of measuring the heat flow, and it flows across a boundary. It usually flows across a boundary due to change or difference in temperature. It is very, very essential in measuring enthalpy. It is one thing that is used to measure the food energy value and also for fuels. So all the labels that you see on food, so this calorie or that calorie, is often measured by calorimetry. So the basic principle, we said that heat flow is movement of heat energy across a boundary. Is that when two bodies of different temperatures are placed in contact with each other, there's a transfer of heat from one body to another body, usually from the body with a higher temperature to the lower temperature until equilibrium is achieved. And the total heat lost by the hotter body is equal to the heat gained by the body with lower temperature. This is on the assumption that no heat is lost to the surroundings. That means you're dealing with an insulated system, which is often what we try to achieve with any form of design, engineering design related to heat. So the heat transfer in the system, whether it's the heat lost or the heat gain, whether you're going from lost or heat, the heat transferred is calculated using the formula MC delta T. We have already said what the MC is. We're going to look at it quickly now. So C is the heat capacity. This instrument is called a calorimeter, and you can carry this experiment out at constant volume or at constant temperature. These are the two measures that are often used. The constant volume one is done in a bomb calorimeter. It's very, again, useful in food and in fuel. So we defined its capacity before. The heat capacity, we already defined it earlier. Let's define it quickly again. And I think we're working on some examples that will delve more into. The heat capacity of a substance as the amount of heat required to raise the substance by 1 Kelvin or 1 degree Celsius. Then you can have the specific heat capacity, and you can also have the molar heat capacity. The specific heat capacity is the amount required to raise 1 gram, and the molar heat capacity is the amount required to raise 1 mole. The heat capacities and specific heat capacities of substances are useful to understand how heat travels across systems, and they are also useful in trying to design materials. I don't know whether I was in this class that I mentioned it. People that are designing pots, they want something that can conduct heat very well. Now, people that are designing engines, they want something that won't conduct heat, so it doesn't destroy the remaining parts of the engine. So all those are related to heat capacities. So we said that the Q can be measured at constant pressure. In such case, we say we're doing a constant pressure calorimetry. More often than not, in the constant pressure, the volume can change. It's expected. It's common in the chemistry labs. It's common a lot in chemistry labs, and in places where the pressure is required to be constant. And why is that so? More often, if you look at the nature around us, things are in the open atmosphere, and in the atmospheric pressure is fairly constant in all cases, in most cases. Whether you are cooking in your kitchen, you're doing so, the atmospheric pressure is often constant. So this is a sample setup of what a constant calorimeter looks like. Something that you can set up in a lab. You get 2 styrofoam cups. You put your system inside the inner styrofoam cup. So the styrofoam cup is to help create some insulation. You put a stopper, usually a wooden one. It puts a stirrer to stir your mixture, and then you observe the temperature difference as your reaction proceeds. The heat of the reaction is calculated as mass times the specific heat capacity times the change in temperature. If you want to do it with number of moles, so you're going to do it moles times the molar heat capacity times change in temperature. So in the bomb calorimeter, you need to put everything in a sealed environment. Which does not allow for change in volume. Simply put, it keeps volume constant. Similarly, the heat absorbed is the same Q as times heat capacity times the change in temperature as the reaction is taking place. In bomb calorimeters, the wires that we have here, ignition wires, usually, as the name implies, ignite to start the reaction. They create some form of ignition to start a reaction. So you listening to the word ignition, we should now think about our car engines. So the engines in our car is an approximate bomb calorimeter. Ideally, what you measure in a bomb calorimeter is the change in internal energy and not change in enthalpy. That's because it's a constant volume reaction or process. However, for most reactions, the difference is so small and is negligible until you are trying to work with a more accurate description. So when you're going for something that's more accurate, then you consider all the small changes in your pressure and volume. Remember that our H is U plus PV. And I also want you to put this into consideration. Anytime you're working on a problem, you always start from an ideal situation, and then you start introducing all the areas of the problem into the ideal solution. Just like we started with ideal gases, I'm sure you've learned about ideal gas and real gases. So whenever you want to solve a problem, you try to make it as simple as possible, and then you gradually complicate it till you get the solution that we are looking for. Okay, so let's try to work an example now. So calorimeter Q is C times delta T. Now this C can be the heat capacity or the specific heat capacity or molar heat capacity, depending on what you're working on. And then you now multiply it by the appropriate variable, whether it's mass or number of moles. So let's work some examples. The first one, a metal weighing 4.2 grams, so mass equals 4.2 grams, was heated to 115. So is heated to means that's the second temperature. When I'm placed in 35 mil.
The mass is 4.82.
It's 4.82.
4.82 grams.
Sorry. Before you crucify me, that's not what I'm going to use. That's what I will use in the calculation. Chai. See, human beings. If you are wrong in the exam or now, you will tell me, Shebi, it's just one small thing now. The metal and water were allowed to come to an equilibrium at this temperature. Assuming no heat was lost to the environment, so we're talking about insulation and adiabatic way, calculate the specific heat capacity of the metal. Consider the specific heat capacity of water to be this. Okay, so initially the metal was weighed, was at 115 before it's now equilibrated to 34.5. Anyway, let's look through the solution so that you would so T of metal, that's different. So let's look at the solution first. So the temperature of the water, looking at water, rose from T1 to T2, that's for water. So that means the heat absorbed by the water will be given as mass of water, specific capacity of water times that. Always, Q is C delta theta. So if you're working with specific heat, is mass times specific heat. If you're working with molar heat, is number of moles times molar heat capacity. excuse me. So the heat absorbed by the water
Ma,
can
please,
be
I
of,
have a question.
go ahead, go ahead.
Ma, but it's not about like what we're doing. I wanted to ask that when are we going to get slides for this?
When
Slides for
you
the
get
class.
it, you get it when you get it.
We didn't get the one for the last class.
And I said you will get it when you will get it. You will get
Okay, ma.
everything.
Okay.
You will get for this thermochemistry together. I'm teaching two parts, and then
Okay.
entropy. You get the thermochemistry before Wednesday.
Okay, ma. Thank you, ma.
Okay. So mass of water, what from the question, the mass of water was not given, but we have the volume of water as 35 mil, and we're also told to take the density of water to be 1 gram per mole per mil. And mass, we know, is volume times density, where rho is density, which is what we have here, 35 mil times 1 gram per mil. So 35 milliliter, yes, mil there. So we have 35 grams. If we substitute these values here that we have, so the mass Q of water, that's mass in 35 grams times the specific heat capacity in grams, so joules per gram per Kelvin. So that's why this was converting to kilograms. And our change in temperature. Painkiller, painkiller, wow, please mute yourself. Okay. So the heat absorbed by the water is 849.76 kilojoules. The principle is that when you put two bodies together in physical constant, and that in such a way that no heat is lost to the environment other than between the two of them, the heat lost is equal to the heat gained. We are trying to calculate the heat capacity, the specific heat capacity of the metal, and we are still going to use the same method where the specific heat capacity is Q over mass times delta T. So that means that the heat released by the metal will be 849.79 joules. So using the same that we have, that the Q of the metal is mass of the metal times C of the metal times the change in temperature, the heat released by the metal is 84.79. The mass of the metal is that. The specific heat capacity, that's what we are looking for. Final temperature. So, sorry, this is final minus initial. Same thing here, final. I'm going to correct it on the slides before I send to you. Minus initial. 34 minus 115. So we use the right one, final minus initial. So this gives us the C metal to be that. Any question? No question. So let's work another example.
I have a question.
Go ahead.
All right. You said that the amount released by the metal is 849.76 joules. So why is there a negative sign after the why is it in the negative form? Is it because that is being released and it's not being gained? So it's negative energy.
Yes.
All right, thank you.
Okay. Energy, there was one slide that I showed, the convention, energy released by a system is negative simply because it reduces the heat content of that system. Okay, I think I have one or two more examples here. In an experiment, is that the example? Okay, this is the example. When a student mixes 50 ml of 1.0 molar HCl and 50 ml of NaOH in a coffee cup calorimeter, our coffee cup calorimeter, that's the constant pressure calorimeter. The temperature of the resultant solution increases from 21 to 27.5. Calculate the enthalpy of the change in reaction in kilojoules per mole for HCl, assuming the calorimeter loses only negligible heat, so it is insulated. Okay, so initial temperature for the system, that's 21.0 Celsius, and the T2 is 27.5. Okay, let's take this stepwisely. HCl plus NaOH. So a student mixes HCl plus NaOH. And from our secondary school, we know that this is a neutralization reaction. It produces water and salt. So if you mix 50 ml of this plus 50 ml of that, the total volume of the solution will now become 100 mils. And because the density of water is 1 gram, the mass will be 100 mil times 1.0 grams. So that gives us 1 gram. Okay. So the temperature initially at 21 rose to 27.5. So we can calculate delta T as 27.5 minus 21.7. 21.0, that's 6.5 degrees Celsius. That is the temperature change. And because of the conversion rate between Celsius and Kelvin, the temperature change is the same in Kelvin as well. So the question is to calculate the enthalpy change, which is Q. Q is enthalpy change at constant temperature.
Excuse me, ma'am.
Yes, ma'am.
I thought that if you want to convert Celsius to Kelvin, you're supposed to add 273.
Okay. So I want to believe you are asking regarding to this.
Yes, ma'am.
Okay, please. Anybody in the class, somebody in the class wants to answer that before I move on, before I give an answer, please.
Because this is a change in temperature, that is why. So if you convert it to Kelvin, you still get the same thing because it's change in temperature.
Okay. Oh, okay, yeah.
Thank you. So we are
Thank
looking
you.
at change in temperature. We are not looking at exact temperature value.
Temperature.
So if we're
Yes,
looking
ma'am.
at, thank you.
Thank
Thank
you, ma'am.
you. And thank you to the other person. Okay, so you recall this is it, or we can simply even say that Q is mCs delta T. The question is calculate enthalpy change for the reaction. So enthalpy change for reaction at constant temperature is delta TH. Is QP. So QP means that it's
Ma,
at
please.
constant.
Ma,
Yes.
please, why is the temperature constant, ma?
Did I say temperature constant? Constant pressure.
Okay,
We're saying
pressure.
temperature change. I wrote it here, please. Constant pressure.
Okay, ma.
So again, the heat change is equal to enthalpy change at constant pressure is equal to QP. Is written as QP. So that's what we are trying to calculate. So Q, we can calculate Q. We can calculate Q as so what's the so temperature increase. So Q is a MC delta S. Say MC delta S. We can calculate it given that. So because it's a according to the question, increases, so it releases it to the system. So we can say that Q, so absolute value of Q is a 2.7. It's negative because energy is released to the system. If we want to look at it from the molar perspective, so calculating the molar heat given off, so all we need to do is multiply by the number of moles, which is 1 mole per liter. 1 mole per liter in 50 mils contains 0.050 moles. So the enthalpy change per mole of HCl is a minus 2.7 divided by 0.05 mole. Let me put that again. Calculate the enthalpy change for the reaction in kilojoules per mole of HCl. So we already know that the enthalpy change for the process that the 50 mil plus 50 mil is 2.7. So how about that's 2.7 kilojoules? That's what we got, 2.7 kilojoules. So we're taking it to per mole. That's where the concept of the molar heat capacity comes in concept. But so looking at the reaction, 50 mil of HCl over 50 mil of 1.0 molar HCl gives us 2.7. 50 mil contains 1 mole times 0.05 liters. That will give us 0.05 moles. I hope that one is clear. Number of moles is a molarity over volume. So if 0.05 moles gives us, if 0.05 mole gives
What?
2.7, so what's 1 mole? 1 will be 1 times 2.7 divided by 0.05 moles. So that's where we obtained 2.7 divided by 0.05 minus 2.7. So that would be 54 kilojoules per mole. Therefore, the enthalpy change per mole of HCl is 54 kilojoules per mole.
Excuse me, is there a way
Yeah.
for us to know if the reaction happens at constant pressure without it being stated in the question?
No, it has to be stated. You have to understand the condition in which so when you start doing experiments now, and for those of you that have done your experiments in secondary school, some experiments in secondary school, You need to write the date of the experiment, and you need to write condition in which the experiment is carried out. Because whenever you change a condition, something changes. Does that make sense?
Yes, ma. Thank you, ma.
Another person is asking that same question on the chat box now. I don't understand why you didn't add 273 to, or was that the same person that asked at that time, Oriola?
Ma,
Please. Yes.
ma,
Yes,
please.
yes.
This 50 ml. I don't still
Mm,
understand. I don't still understand the way you derived it to 0.05 mole. I don't still understand that side really well.
okay. So let me, okay, so that's nice. So some of you are helping each other out in the chat box. Thank you. Let me see. Nnamdi, Egbuna, what's your question, please? So that I answer them together.
Ma, I'm kind of confused with the nature of the reaction. If the solution is gaining heat, it's not meant to be endothermic because the thing increased from 21 to 27, and yet it's still exothermic, meaning that it lost heat.
Okay.
No, exothermic.
Okay.
Ma, please, I don't understand that last part. How you got minus 54 kilojoules per mole?
So I'm coming to that one. So let me see. The temperature of the resultant solution increases. Okay, so let me explain that to you. The temperature increases. So that increase in temperature is given off to the surroundings. Now, endothermic, you are adding temperature to the system. You're adding heat. To the person that asked the question. Sure, you understand?
Yes, ma. Yes, ma.
So this one, the system increases its heat, and that heat that it increases, it produces that heat. That heat is given off to the surroundings. Does that make sense?
Yes, ma. Thank you.
Okay. So for the person that said they don't understand this last part, let me see, any extra space here. So what we said is that 50 mils of 1 molar HCl solution is what is used for the reaction. In that 50 mil, how many moles of HCl do you have in there? Can you get it? The person that asked the question, please, let's move together. So
Okay.
50 mils of a 1 molar solution, how many moles do you have in that? Hurry up, we still have something to cover today, because the last time I can teach you will be Wednesday. You will have to go and read the other things.
Ma, we have one more, ma.
No, it's not 1 mole.
No,
In 50 mil of 1 molar, it's 1 molar is 1 mole per liter. So you have 1 mole in 1 liter. In 1 liter. 1 mole in 1 liter. So 50 mil will be how many moles?
15. 1 mole in 1 liter.
You know that
0.05.
0.0.
Yes, so that's why we
mole.
got this. So that's where this came from. It is this 0.05 mole that gave off this minus 2.7 kilojoules of energy. Sure,
Okay,
you
ma.
understand? So
Yes, ma.
if
Yes, ma.
0.05 moles gives us 2.7, how much will 1 mole give off? Because the question says we need to express it in kilojoules per mole. Per mole is 1 mole, right?
Yes, ma.
Okay, so we can move on now, right?
Yes,
No, ma.
ma'am.
No.
Ma.
Let me see.
I have a question.
Okay, move, come ask now. I told you that we need to quickly do something. You are still
Okay,
you are still waiting there.
how do we get 1 mole equals to 1 mole per liter of the HCl solution?
What does that mean? 1 mole equals 1 mole.
In the lower part.
Read everything together. You can't just read one line and move on. To express the enthalpy change on the molar, we use the fact that the number of moles is given by the product of volume. Read it together. Not
To
just
express,
that's
okay,
what I
to
just expressed. 50 ml, you have a 1 molar solution. That means 1 mole per 1 liter. In that 1 mole, you take 50 ml. How many moles do you have in that 50 ml?
yeah, I get that part. The other part and concentration, 1 mole equals to
That
1
is,
mole.
read it from here. Read it from here to express. Don't take
To,
that line. That's a complete statement. What you are reading is a phrase.
okay. To express the enthalpy change on a molar basis, we use the
So,
fact that
the fact that the number of moles of HCl is given by product times volume. So 50 ml equals 0.05 liters. And
yeah.
1 molar, what is molar?
Mm,
Unit of expressing concentration. What is molar?
Mole per dm cube.
What is this one that we have here?
okay, mole
Mole
per liter.
Hess's law, another way to calculate delta H. Hess's law is another way to calculate delta H, especially useful when you don't have the delta H for a particular reaction and you need to use it. So Hess's law states that if you have a reaction, let's put it that way, you have a reaction A going to B. It is possible that A goes to C first before it then goes to B. Or maybe A goes to C, C then goes to D, goes to G before going to B. These are different reactions that you have. Or it goes a totally different route. A goes through E, H, and then to B. The long and short is you want to perform a reaction where you obtain B, a new product from A. Depending on the result, on what you have, you don't know how to, you don't know, you want to calculate delta H for that reaction, but you don't have some other resources. So Hess's law states that the overall enthalpy change for any reaction is equal to the enthalpy change for all the individual steps. So the net displacement from a certain place to another place, it's the same regardless of how you go about it. The overall, the net change. The reason for why we can do that is because, like we've said, that enthalpy is a state function. That is the major reason that can be. So if I want to put it in a diagram, so A, initial reactants going to final product. A can go through C, which we call an intermediate, to final product B. It can also go through D, which goes to another intermediate. So C, D, and E are called intermediates before you arrive at your final product. Another way you can put the Hess's law is that in a reaction consisting of several steps, the delta H for the final reaction is the same as the sum of the delta H of all the small steps. Delta H is the reaction that we are interested in, delta H1. From this diagram, delta H1 is the reaction that we are interested in. According to Hess's law, delta H1 is a sum of delta H2 plus delta H3, because if we go through C to B, we arrive at, if we go through C to B, we arrive at what we are looking at, A to B, but we have gone through one delta H1 and delta H3. So why is this useful? Over time, and the big thing that people are talking about now is data. That's because so many data have been curated over time. There was a time that to get your PhD or to get your master's, you need to be able to generate data. And that generator has been stored. So over time, the delta H of several reactions have been generated. And some, you cannot generate them easily, but you can relate them together to get what you're desiring. So it cuts down on the number of experiments to do or to start from, rather than starting from scratch again. Again, your delta H1 is also equal to the sum of delta H4 plus delta H5 plus delta H6. So this is one example of a real chemical reaction. This is a reaction of combustion of methane. Combustion reaction is a reaction where with oxygen. Combustion of methane, this is methane, CH4. It is a thermochemical reaction because we have indicated the states of the reactant, and we have also indicated the delta H1 of the product. Okay, so this reaction, the combustion of methane, the desired product is CO2 plus H2O, liquid water. This reaction can go down in steps. CH4 goes to CO plus H2O first. So this is an incomplete combustion. This one is incomplete combustion, but you still have more oxygen, and then it goes for that, reacts more to get your final combustion product. So if you look at it, the delta H2 for this first step, which is minus 607, if you add it to minus 283, you will get negative 890 kilojoules, which is the delta H for the whole. If you miss a class, the videos were shared. The YouTube is there. Go through the class. Don't come and ask what is a state function. What's something that we have done 2 classes ago. Any other question? So let's work an example. Class is almost over. So we're given this reaction. C plus O2 plus CO2. So this is what we have. We know that the enthalpy change for this reaction is minus 94, and the enthalpy change is for this one is minus 136. The question is, determine the enthalpy change for the following reaction. So this is carbon plus half oxygen to give CO. So the normal thing is to compare the given equation. So you compare the given equation for which you want to determine delta H, you compare it to the available equations. That's the one that was given. If we look at it, carbon, let's compare it with equation 1 first. C and C. So when you are trying to compare, you want to compare the things that are on the reactant side. That would help you to determine whether you want to flip your equations or you don't want to flip it. And then you also want to note the number, the stoichiometric ratio. So the ratio of the carbon. So if we compare the given equation with equation 1, we have carbon, oxygen. Okay, so we have CO here. CO is not here, so we look for where we have CO. So because of that, we can still leave equation 1 the way it is. Equation 2, carbon. So carbon monoxide is there. Carbon monoxide is on the reactant side here. So for the carbon monoxide to be on the reactant side, this one must align with that. So we are going to reversed. So this is reversed. We are going to reverse equation 2. Also, we're going to divide it by 2 because we have 1 mole here. This is 1 mole. So we're looking at the stoichiometry now, but we have 2 moles here. So let's do this that we have just said. If you reverse equation 2, you have 2CO2 plus CO plus O2. So our CO is now both on the product side. Because we are reversing it, the delta H for the reaction will change sign from negative minus 136, from negative 136 to positive 136. Also, we have 1 mole here and now 2 moles here. So again, whatever equation you are given must align with the equation for which you are trying to solve the problem. So what do? We divide it by 2. So if we divide it by 2, so this becomes 1, 1 half. And delta H will be divided by 2 because H is an extensive property, meaning it depends on the content that you have, amount of substance that you have there. So this becomes our equation 3. Or if you want to call this 3 or 4, just to keep track of things. So when this becomes equation 3, we can add, if we add equation 3 to 1 now, so this is equation 1, this is equation 3, C plus O2 going to CO2, CO2 going to C plus half to O2. Okay, C plus, there's no C here, C stays the same. There's no O2 here, but there's half O2 here. So this, okay, all right. So that's CF plus CO2 plus O2 going to CO2 plus CO plus half O2. As long as you are going to add the 2 equations together, you will need to add their delta H's together as well, according to Hess's law. So this is carbon dioxide is here, carbon dioxide is here, cancels off. Carbon is here, so that there is no carbon, but there's oxygen here, 1. There's oxygen here, that is R. Those of you that are chatting in the chat box, please stop it, because I'm checking it to see if there are questions there. There's no question like, I don't understand. You need to ask specific question. Shoyinka, you need to ask specific questions, please. There is nothing like, I don't understand. Can you go over it again? So you have 1 O2 here, and then half O2 here. The net will be, so if we subtract half O2 here, we have 0. If we subtract half O2 here, we have half O2. 952. So I'm going to skip. I can't skip. I'm going to skip an example. Oh yeah, questions, please. 5, 4, 3, 2.
Mom, I don't understand
I
the
don't
question.
understand.
Marcus, I don't understand from the beginning.
You would have to look at the video again, Neo. Please explain the last equation. What is the last equation?
From the
At
beginning
the
also.
place where you
From
wrote
the
adding the
beginning.
first and 2
Sorry,
first
ma.
equation.
Sorry, ma. Just this example. I'll just like go over it again from the start. Like brief overview, so we could just catch up for people.
You know,
who
let me tell you what this would mean. If by Wednesday I cannot complete entropy, you would have to read it on your own. Okay?
Okay,
So
ma,
it's
please.
better.
Why did you
Please, what?
minus half oxygen from both sides?
Why did I subtract oxygen from both sides? Okay,
Yes.
so we're given these 2 equations and to determine the enthalpy change of that reaction. When you have such a thing, you would have to align this, you have to align the given equations with the reaction that you are trying to do. We know that you can add delta H's together for several steps because it is a state function according to Hess's law. Okay. So if we compare this our equation CS, this equation, if you compare it with the first one, CS plus O2 to give CO2. So you have CS, carbon, oxygen gas, and oxygen gas. So we need to get rid of carbon dioxide, Rabi, and we need O2 to be half. Beautifully, coincidentally, we are given another equation that contains oxygen and CO2, which is the second equation. The second equation, that's 2CO plus O2 to give 2CO2. Now, this second equation has CO2 on this side. By elimination, you can subtract or add. If you want to eliminate this CO2 from this expression, it has to be on the reactant side. We cannot reverse equation 1 because equation 1 has carbon solid on the reactant side, which is what we are trying to determine. So to eliminate the CO2, we're going to have to reverse. Are we following? Those of you
Yes,
that are
ma'am.
So
Yes,
because
ma'am.
this
Yes, ma'am.
CO2 is on the
Yes, ma'am.
product side, we will have to reverse that equation. If you reverse it, you have 2CO2 going to 2CO plus O2. And because you are reversing it, you will also change the sign of delta H. So once you do that, compare it to what you have, you would note that you only want to get rid of 1 mole of CO2. Because you want to get rid of 1 mole of CO2, you will divide the new equation that you've reversed by, what do you think you can divide it to get CO2? You can only divide it, but you can multiply it by half or divide it by 2.
By
So if you
2, yeah.
divide it by
By
2,
2.
you get CO2 going to CO plus, this is now 1 over 2.
Or 2.
So that is what we have here. And because we have divided it, this will also be divided. So dividing that, if you divide that, this is your equation 1 now, C plus O2 going to CO2, and this one is CO2 going to CO plus half O2. You have the delta H for each one as given. If you combine these two equations together, we arrive at this big one. C plus O2, this is O2, plus CO2, plus the CO2 here on the reactant side, plus this CO, plus this half O2. There's one CO2 here and another one CO2 here, so that cancels off. 1 minus 1 is 0. There's one O2 on this side, and then there's half O2 on this side. This one is greater, so if you bring this one to this side, it becomes half O2. So that's what we have here. This equation
I have
is
a
like
question.
this. How do you
But
subtract 1 from half or what?
no, I have a question.
You don't have a question. If you have a question, you will ask it.
Okay.
So
Are you minusing equation 2 from equation 1 or equation 1
Yeah.
from
what do you
equation
look
2?
at it? Look at it. Look at it. Look at the expression. What do you think? If you look at this,
She
Abi,
only added
because
the two equation now, and then
Exactly.
subtracted
it is
this
written
half
here,
mole of
adding the
oxygen from both
first,
sides of the equation.
adding to the first equation. It's 9:58, and I want to believe you have another class now.
Yes, ma'am.
That means you would have a lot to read on your own.
If we're adding, why are we minusing 1 over 2?
What do you think? Please, I like
Because
it
there's
when
oxygen in both sides of the this equation. There's oxygen in the reactant side, and there's oxygen in the
Let
product
her
side.
explain
You have to
herself
subtract
now.
that oxygen from both
Let
sides
the
of the
teacher
equation. How
explain
many times have you
herself
cleared
now.
this one?
no, he
Ah,
has given you a good explanation. He has given you a very good explanation. Write this thing out yourself and look at it. I can't always give you everything. The teacher cannot always give you everything you need. You need to reason out some things. See you all on
Yes.
Wednesday. That will be my final class.